Hello, everyone, and welcome back. In the previous video, we talked about absolute convergence and how, when your series is absolutely convergent, it implies that your original series converges. Now, we saw a particular example of this with the harmonic series, where we know that the harmonic series is not absolutely convergent, and therefore, we couldn't say anything about the alternating harmonic series. And what I offhandedly mentioned in the previous video was that actually the alternating harmonic series converges. And the question is, how did I know that? Well, that's what we're going to talk about today. We're going to talk about alternating series. And typically these alternating series don't converge absolutely, or at least the ones we're going to be interested in, but they do converge as alternating series where we're alternating between adding a term and subtracting a term. Let me show you what I mean. So the alternating harmonic series is given like this: 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 and so on. And so the general term here is minus 1 to the n plus first power divided by n. So this is the alternating harmonic series. Again, what I just said was that this thing does not converge absolutely, right? If you take an is equal to minus 1 to the n plus 1 divided by n, then the absolute value of an is equal to 1 over n, and the sum of the absolute values is just equal to the harmonic series, which we know goes to infinity. Now, what I want to give you is a new tool that we can use to test for convergence, and it is called the alternating series test. So we have another test for convergence. Particularly, this is going to be useful for series that are not absolutely convergent. So let me give you the theorem and we can talk about it. So this is the alternating series test. Okay, so it says that the series, so we're going to write it like this. We'll write it as the sum from n equal 1 to infinity of minus 1 to the n plus 1 times un. So your whole an term is everything in there, minus 1 to the n plus 1 times un, which is the same as u1 minus u2 plus u3 minus u4. So you're alternating between adding and subtracting terms in here. Well, then this thing converges if the following are true. So we have a list of conditions to check. So the first condition is that the UNs are all positive. So we actually are adding and subtracting terms, right? We don't want to be able to mix up adding and subtracting here. So you really are taking positive U1 and subtracting positive U2, then adding positive U3, and so on and so forth. Also, the UNs are eventually decreasing. So we saw that one of the last examples that we did in the previous video, we saw that actually the ANs were increasing, and we could use this to figure out that our series diverged, even when I believe it was the ratio test told us that it didn't work. So you can see that this is clearly going to be important. We need to have that these things are decreasing. And what this means properly is that UN is greater than or equal to UN plus 1 for all n greater than or equal to n for some integer n. So we've seen this notation now a few times. Essentially, remember, this is describing the tail, right? It's telling us, eventually this happens. We don't care about the finitely many at the front that it doesn't work for. And of course, we need un going to 0. So that is necessary by the test for divergence, right? We need to have that we are adding up smaller and smaller terms every time we go through this. Okay, so how can we use this to check if the alternating harmonic series converges or diverges? Well, let's look at an example. So the first example, the application of this, the alternating harmonic series. So n equal 1 to infinity minus 1 to the n plus 1 divided by n. This implies that un is equal to 1 over n. Clearly, so we can see that maybe checking 1, un is definitely positive. Checking 2, since n is less than or equal to n plus 1, this tells us that 1 over n is greater than or equal to 1 over n plus 1, which tells us that un is greater than or equal to un plus 1. So we are eventually decreasing. We're actually decreasing for all n greater than or equal to 1. So my capital N is just 1. And clearly, you can see that un is going to 0 as n goes to infinity. So therefore, by the alternating series test, the alternating harmonic series converges. So I think that's a really cool result, right? Because the harmonic series is like the one that we use all the time to talk about a divergent series, right? It's sort of the canonical example of a divergent series. But what we're saying is that we alternate between adding and subtracting terms, this thing actually converges. And we'll get into this later with some of the more advanced methods that we'll be talking about. But in fact, this thing converges to the natural logarithm of 2. So that's going to require some work on power series, which will be the subject of some coming videos. But nonetheless, I'll give you a sneak peek. We'll talk about this. This thing converges to 2. So it's kind of exciting. Okay, so the real, if we look at the conditions of the alternating series test, 2 of them are pretty easy, right? The first one, checking if the UNs are positive, easy. Second one, the third one, checking if UN goes to 0, that's easy. The hard one might be the eventually decreasing. But it turns out that we can use functions, right? When we hear the word decreasing, we think of functions having negative derivatives. Well, we can do exactly that, or we can use that knowledge to check these cases. So let me show you what I mean. Let's suppose we've got this series, 10n divided by n squared. Sorry, there's a minus 1 to the n plus 1 out front. It's an alternating series. And then times 10n divided by n squared plus 16. Again, you can check this thing is not absolutely convergent because you can compare it with 1 over n, the harmonic series. So this thing, if you didn't have the minus 1 to the n plus 1, the alternating part, this would not converge. But what we're going to show here is that actually it does converge. Clearly, so the UNs are equal to 10n divided by n squared plus 16. And these things are all positive. It converges to 0. So really all we have to check is decreasing. So is UN eventually decreasing? Well, the way that we can check this is we can notice that if we define the function f of x, so we remember some of this comes from what we talked about with sequences, right? So we can think of these as putting them into functions, just evaluating them at single points, single integer points. So let's think about this right here. So that un is equal to f of n. We can check whether or not the function is decreasing. And if the function is decreasing, that means that means the sequence is decreasing as well. So we can use the quotient rule. So I hope you haven't forgot some of your derivative rules here. You can find the derivative of this thing to be 10 times 16 minus x squared divided by x squared plus 16 all squared. And you can easily see that f prime of x is less than or equal to 0 for all x greater than or equal to 4. Right? So that just comes from solving this thing equal to 0. It's really just determined by that 16 minus x squared in the numerator. But then un is decreasing for all n greater than or equal to 4, right? Because what it tells you is that the function is decreasing. And so, the value of a previous x to a next x that are bigger than 4, then the function at the first one is going to be bigger than the function at the second one. So because we have this relationship right here, that really the function evaluated at the integers gives us our sequence, this tells us that un is decreasing for n greater than or equal to 4. We can put a little note in here that capital N is equal to capital 4. And so now we've used a little bit of calculus to get exactly what we need out of this thing. And so therefore, this sum converges. So minus 1 to the n plus 1, 10n divided by n squared plus 16 converges by the alternating series test. Let's put it down here. So this is great, right? It's not really that difficult to apply this alternating series test. And like I said, you can turn it into a calculus problem. Really, the one that should or could potentially give you a headache is that second condition, because it's relatively difficult, right? You need to check whether or not the sequence is eventually decreasing. But from the example that I just showed you, well, we can use all of our calculus knowledge to solve this. Okay, let me finish this up by giving you a way of estimating the value of these sums. So if you maybe want to put this into a computer and you want to check, you did the math, you were able to show that these things converge, you want to know what they converge to, at least, as a decimal expansion. Well, we can estimate it up to a certain error, just like we did with, say, the Simpson's rule or the trapezoidal rule for estimating integrals. So here we have another theorem, another result, and this is the alternating series estimation theorem. Okay, so let's say let the sum here. So an alternating series satisfy the three conditions of the alternating series theorem. Right, so we are going to assume that it satisfies those conditions from the alternating series theorem, then it will converge, right? So then there is an L in R such that the sum here is equal to L. So I'm just setting the stage first. I'm saying that this thing actually converges. And then the partial sum Sn, which is adding up the first n terms. Remember, we talked about this way back at the beginning when we started talking about series. Minus 1 to the n plus 1 un satisfies L minus Sn in absolute value is less than un plus 1. Sorry, let's make that less than more prominent. But basically what this says is that you can approximate, or you can govern how well you can approximate the sum of an alternating series. Now look at the three conditions of the alternating series theorem. The last one says that the UNs are going to 0. So they're getting small, right? That's the definition here. And so what this is telling you is that if you want to get really close to what the sum is, add up the first n numbers, get the first, the partial sum, Sn, and then you are within un plus 1 of the true limit of that thing. So if un plus 1 is super, super small, maybe it's like 10 to the minus 3, then you're within 10 to the minus 3 of the limit. So you got the first 2 decimal places done, right? This is a way for you to control how good your approximation actually is here. Now, let me show you a particular application of this where we know what the sum is so that we can actually have some measurement of how, how to see if this is working or not. Okay, let's do the sum. Let's start from 0 to infinity, minus 1 to the n, 1 over 2 to the n. This is the same as saying 1 minus a half plus a quarter minus an eighth plus a 16th minus, I'm gonna write up a lot of terms here just so we can so we have something to visualize while we're talking about this. 1 over 64 minus 1 over 128 plus 1 over 256, and that's good enough. Okay. So the theorem says that if we truncate at a certain number of terms, then we are going to be within the next term. So for example, S8, the 8th partial sum, so that would be adding yourself all the way up to n equal to 8. So that is adding up to, so maybe I should draw this. This is equal to S8, adding up to n equal to 8 here. Well, you can throw this into a calculator. Maybe you can design a computer program to get this for you. So here's what it is. It's 0.66 and then 40625. But also, this is a geometric series. So a geometric series. So I know what its sum is equal to. I can see that this thing is equal to 1, the first value, divided by 1 minus, and the ratio is minus 1/2. So this is 1 over 3/2, which is equal to 2/3, right? And just so we remember, this is like 0.6 repeated. Sorry. Okay. So clearly we're underestimating because S8 is at 0.664. So then L is equal to 2/3. And the difference, L minus S8, is equal to about 0.00260. So I'm going to give a lot of decimal places just so we can see what's going on. So on. So 2 times 10 to the minus 3, right? That's really what we should see here. And un plus 1 is equal to 1 over 256, right? Because this is, maybe I'll just put it in a different color. This is equal to U9, right? So 1 over 2 to the 9. which is equal to 0.003900625. So as the theorem said, the partial sum S8 is within U9 of this limit. So that's good, right? Like, think about how nice this is. This tells me that if I want to approximate the sum of this infinite series, all I needed to really do was use like 8 decimal places to get, or sorry, to use S8, the partial sum of 8 terms, in order to get at least 2 decimal places correct here, right? And if I wanted to, I could keep going. I could use the first 100 elements to get S100, and then, you know, my error is bounded by U101, which is 1 over 2 to the 101. That is a very, very, very small number, right? And if you think about this in terms of computing power, you know, adding up 100 numbers is really, really easy, right? This is something that a computer can do, you know, lightning fast. So you can get, you know, incredible approximations, and you can be guaranteed that they are sufficiently close to your error because of this alternating series approximation theorem.